All right, it's 10 o'clock, folks. We'll get started here. So what I wanted to do was go through the first half of test 2 and look at problems similar to what you would have seen in the videos, and to then apply that to the different things that you'll be doing for the practice test as well. So we're starting out here with titration curves. And, you know, obviously I'm hoping that you've read the videos here, watched the videos that refer to all of this before coming here. But if you haven't, I'm going to give you just a very brief overview as I do each question, just a very nuts and bolts kind of thing. But I still feel like it's worth doing. I still feel like it's worth doing the videos as well, and not just trying to focus on the problems. All right, so as you know, this will be recorded and it will end up being posted on in the Zoom folder. All right, so we're going to start off here with titration curves. Does anybody have any general questions first about the titration curves question, or titration curves in general? Okay, well let me go through and just give a very brief background to this. What we're looking for here is a titration curve between a strong base and a weak acid. So you'll notice in the problem that strong base and weak acid are mentioned. So we're actually told that we're dealing with a strong base or a weak acid. There is a video about this. It didn't have a link set up initially for it, but a student alerted me to it about a week ago, and I did fix it. Something about strong acids and weak bases, but that link's been fixed. So if you had trouble getting to that, it's fixed now. It has been for about a week. All right, let's look at the process here that we're dealing with. You all can hear me, right?
Yeah.
Good. Thank you. The situation involves having a burette, which I don't draw very well, and a flask. And when we're titrating something with something, let's say we've got something in the burette, I'll put A in here. And if we're saying we're titrating A with B, you've all done titrations before, we know that A is in the flask and B is in the burette, which is kind of important. So here we're looking for the titration curve for titration of a strong base, LiNH2, with a weak acid, acetic acid, or CH3COOH. So we know that lithium amide, or LiNH2, is in here. We know that the acetic acid is in the burette. So initially, before anything gets started, we know that there's no acetic acid in the reaction mixture in the flask. All there is just that LiNH2. And we do have a little bit of knowledge here about the pH scale. And this is really all you need to be aware of. And that is that this is strong base, this is strong acid, this is neutral, this would be weak acid, and this would be weak base. Does anybody have any questions about the pH scale? Everybody's okay with the pH scale? Okay. So when you're drawing a titration curve, you're going to have on one axis, it'll be the pH as the solution, and on the other axis, it'll be volume of B. In this case, it'll be the CH3COOH. It's whatever's in the burette. And even though I don't put any numbers here, this is effectively 0 on the x-axis. So at 0, we're looking at none of the stuff being added from the burette at that point. So the pH is strictly due to whatever's in the flask. And if we're told, and you always are, whether it's a strong or weak base or weak acid or strong acid, then you know from the question what the starting pH is going to be. And it's going to be, I'm going to put 13, but 13 or 14 is fine. Does anybody have any questions about how I know that we're starting out at pH of 13 on a curve like this? All right. It also makes sense that after a time when we've neutralized all of the base that's in this flask, all we're going to be left with is acid, and we're going to end with this pH that's going to equal whatever this is going to be here. And it says that's a weak acid according to my diagram on the pH scale there. That's going to be a pH of 5. So that's going to be the end there. And then the curve is going to look like this. So it starts at 13, ends at 5, and we get this large drop in the middle here. And in the middle of that, that's the equivalence point. Excuse me. Let me get rid of that. That's the equivalence point, which is when the moles of acetic acid added is equal to the moles of the base. So that's what's special about that point. But you'll notice there's a very precipitous drop in the pH at that point once all of the base has been eaten up by the acid. And once all of that's gone, then all you're left with is the products of the reaction, which we'll get to in a second. But anyway, that's what it's going to look like. It's very easy to determine the starting and ending points. The starting point, first of all, know what's in the flask, what's in the burette. We're always starting with the pH of whatever's in the flask, and we end with the pH of whatever's in the burette. And then the curve looks like this. Or if it's going the other way, it'll look like that. But it's always going to be this S-shaped curve with this precipitous drop in the middle. And in the middle of that drop, that's going to be the equivalence point, where you've got equal numbers of moles of acid and base. Does anybody have any questions so far?
Is it always true that acids and bases neutralize each other when they have equal moles?
Yes.
Okay.
Absolutely. Now we can determine the pH at the equivalence point, and we can estimate it by doing the average. So the pH at the equivalence point here is going to be about 9, which can be worked out 13 plus 5 divided by 2 is 9. That's going to be important later, but we'll get to that. But yeah, but the pH at the equivalence point is always going to be sort of like the average between what you start with and what you finish with. Now in the lab, and I'll be doing the lab Zoom session at noon as I usually do, we're going to be dealing with pH of buffer solutions, and this is actually relevant to what we're doing here as well. And I'm just going to give you a very brief overview to tell whether or not we're going to have a buffer region on a titration curve or not, and what a buffer region actually is representing. So let's just look at, first of all, what the definition of a buffer is. A buffer is a mixture of a weak acid and its conjugate base, that resists changes in pH.
I don't see anything being written down.
You don't? Let me share this. Let me make sure I'm sharing the right screen here. I am sharing the desktop, so I'm not sure.
It was showing.
It was? Okay.
Oh, okay.
Adrian, you all right?
Yeah, I see it now.
Okay, all right.
Thank you.
Okay. That resist changes in pH upon addition of a strong acid or strong base. Now, we'll actually be doing this in the lab, and I'll be talking about this during the Zoom session as well, and I'll get into this. But buffers are incredibly important. Our blood is a buffer, and the reason our blood is buffered is so that we don't get changes in pH of our blood that are drastic, because if the pH of our blood changes, then our enzymes tend not to work properly, because our enzymes are really pH dependent on the way that they react with things. And, you know, if your enzymes aren't working properly, then you could be in a lot of trouble. So that's what a buffer does. The thing is a combination of a weak acid and its conjugate base. So you can tell from the question here, and you will in the other questions as well, whether you have a weak acid present or a weak base present, and we do. So we're certainly into a realm where we can talk about that. But look at when it happens. It happens when, upon the addition of a strong acid or base. So if you've got a weak acid and you're adding a strong acid or base, then you know you're going to get a buffer region. But look at what's happening here. We're adding the weak acid to the strong base, not the other way around. So I wouldn't be expecting a buffer region on this one. So it's only when you're adding a strong acid or strong base to a weak acid or weak base that we end up getting a buffer region. What does a buffer region look like? Well, if we did have a buffer region, here's what it would look like. You'd have this kind of flat area where the pH didn't change much. But the best advice I can give you is to look at what's down here. And if that's not if that volume is not of a strong acid or strong base, you're not going to get a buffer region. So the only times you get buffer regions is when you're adding a strong acid or strong base. Here we're adding a weak base we're adding a weak acid to a strong base, so we're not going to get a buffer region in this case. I do have a video about that as well. I think I explain it pretty well in there too. But this is the very quick and dirty way of telling if you have a buffer region. So there'll be a volume of a strong acid or strong base here in this titration curve. Does anybody have any questions? So I'll just write there, no buffer. Any questions about that? Okay. You can never have a buffer if you're adding a strong acid to a strong base. It just can't happen. Okay, it's impossible. You can never get a buffer in that situation. So if you're adding HCl to NaOH, you never see that nice plateau that you would get if you were adding something and it was buffering. All right, the next part, and I think this is probably the hardest part of the problem. Doing the titration curve usually doesn't annoy people that much. Not generally. What does annoy people though is the reaction we're getting here. So let's look at the reaction, and we're looking for the reaction at the equivalence point. Remember, that's when equal amounts of each have been added. So let's take a look at this one here, LiNH2 and CH3COOH. Let's look at some clues we're given in the problem though. We're told here that LiNH2 is a strong base, so I'll write SB above it. And we know that this is a weak acid. Remember, we know this because we're told it. You always will be. You don't have to have this memorized list of what's a strong acid or a strong base or a weak acid or a weak base. I do give some guidance for that, but it's not necessary for the problem because I tell you in the problem. Now, if something is an acid, by definition, it produces H plus in water. Now, bases also produce OH minus when put in water, but I'm not going to go into that here. That's another consequence that I want to. That's not really relevant to this kind of problem. But when we're looking at, if you had this here, you know what the story is. if you add NaOH plus HCl, you'd know that NaOH splits into Na plus OH minus, and you know that HCl splits into H plus and Cl minus, and then you know that these join together and then these join together. It's called a double displacement reaction, and I know you've seen those before, and that's how we end up getting water and a salt out of that kind of problem there. But all we're really doing is just applying the same thing here. It's just a little bit more advanced. If I'm told that this is a weak acid, then I know it's going to split into H plus and something else. Now that something else is always whatever it is without the H, but with a negative charge on it. I'll stop there for a second. Is anybody confused about how I know how that weak acid splits apart? Okay. The other part here will split into the metal ion with a positive charge, and then whatever else will have a negative charge. And that's how you'll do that. Now, I said earlier the bases will form OH minus when you put it in water. And sure, if you put NH2 minus into water, yes, it will form OH minus, but we're not showing that here. We're just going to show the direct reaction between these species. So if you look at what happened with the NaOH and the HCl, you can see the H plus and the OH minus add together to give water, but it's the positive and the negative that are joining, and then the positive and the negative that are joining over here as well. So again, we know that it's going to be the Li plus will join with this, and the NH2 minus will join with the H plus. So the products of this process will be LiCH3COO and NH3. So those will be the products. That's what we're expecting at the equivalence point. Does anybody have any questions?
Do you do anything with the charges in the products?
No, because everything at the beginning is neutral. So we're expecting everything at the end to be neutral as well.
Okay.
Now, if you wanted to, I suppose you could express this as Li plus CH3COO minus, but I really prefer it if you just put it together as a single compound, because that's what it is.
Okay.
All right. Anybody have any other questions about that? I'm going to go through plenty more examples of those. That tends to be a very annoying problem on the test, but I want to go through it in the context of what you'll be seeing. What I'm trying to do here is just give you the whole picture of what a titration problem looks like. The rest of it, number 2 and number 3 there, are basically based on the titration curve. The last one there, we do have an equivalent question to that. And what we're looking at here is, it says, what would be the best indicator to use? And the best indicator will generally bracket the equivalence point. Now, what we said for this previous one, if you remember what the equivalence point was, we started at 13, we went to 5, the equivalence point was 9. So the best indicator here would be probably phenolphthalein, because that brackets the equivalence point. But you'll have that list there in front of you. You don't have to memorize that. So it's just it's a matter of knowing just where the equivalence point is for that question. Does anybody have any questions? All right, let's go take a look at the practice test, or the ungraded copy of the practice test. Same story as last time. I was pretty impressed. A lot of people did really well on test 1, which was fantastic. They took my advice and they did the ungraded copy a lot of times, which was fantastic. It's what I want people to do. All right, so let's look at question 1 here. And you can see that we're looking for the titration curve for a weak base with a strong acid. All right, so with that, I think it's probably good to draw a little bit of a diagram here, just to make sure that you're clear about what you're doing. And then you can match it to whatever you see in these diagrams. And as you can see, there's a lot of them here. There's a lot of different choices. And some of them have buffer regions and some of them don't as well. So it's important to be understanding where this is going. So a little bit of just a picture, just to give you an idea of what's going on. It says weak base titrated with strong acid. Yeah, so we've got the weak base is in the flask or the beaker or whatever. And there's my horrible burette. The strong acid's in the burette. All right, so let's see how that should look. We know it's going to be pH, and we know down here, this is going to be volume of strong acid. See, whatever's in the burette is always going to be on the bottom there. The initial pH is going to be the weak base, which is going to be 9. And the final pH is going to be 1, because that's the strong acid. And then we draw in our, oh, that's horrible. Let's try it again. There we go. That's better. And now we've got to determine if it's a buffer region or not. Now, what I had said earlier, I know I've erased it, but the definition of a buffer was it's a combination of a weak acid and its conjugate base that resists changes in pH upon addition of strong acid or strong base. And as you can see, we're adding strong acid here, and we do have a weak base in that flask. So I would be expecting a buffer region here. So I would be looking for the option that had the buffer region. Does anybody have any questions about this here? So for this one, let's see, 9 to 1, see, that one doesn't have the buffer. There he goes. That would be the answer I'd use. Does anybody have any questions? You all clear on this? Maybe this is your time, folks. I'm not trying to drive the boat here. All right. Question 2. This is where we apply that issue I was talking about earlier with the reactions. So for something like this, you've got HClO4, and you see, notice how I tell you it's a strong acid or a strong base or a weak acid or a weak base. That's important here. So for this one, I've got HClO4, and I'm telling you it's a strong acid. And then I've got CH3Li, which is a strong base. So how do we apply this? Well, if it's a strong acid, I know it's going to be split into H plus and ClO4 minus. Is anybody confused about how I know that? It's really important. Okay. And the other part is going to split into CH3 minus and Li plus. I know this because anytime I've got Li or Na or K or anything like that, it's always going to split off as a metal, and it's going to be the positive charge there. So that's going to have the H plus will join to the CH3 minus, and the Li plus will join to the ClO4 minus. So it's always the positive and the negative joining together, even though you might be more used to this insides, outsides business. It all depends on how the compound is being expressed initially. Does anybody have any questions so far? So that would be LiClO4 and CH4. And that would be the answer that you would end up putting in that box. Does anybody have any questions? You're all completely fine.
So
yeah.
It doesn't matter if the answer is balanced in regard to the beginning.
No, it is balanced. What's the issue, Nathan?
Sorry. So like we're like just we have the product of HClO4, but we have a H4 in our solution, so we are getting like more hydrogen in there. And I guess we have in the
well,
original.
no, you see, it was CH3, and it was H. When you add one H to CH3, you get 4 H's.
Oh, I see. I see what I did. Yeah, my bad.
So, but if you had written HCH3, I would be hunky-dory with that. Now, the test might not be, but I would be. So if you wrote to me via email and said, well, look, I put HCH3 in there, I'd go in there, I'd correct it. I'd say, yep, no worries.
I just misread that.
Okay. But they are balanced. They're all balanced. Does anybody have any questions? Okay. I'm going to re-roll this in a second. Question 3, that's the one with the indicator. And you can see weak base with strong acid is the, and I think, well, that actually matches what we have up here, funnily enough. So we know the pH at the equivalence point is 5. So you should probably do a curve for this, and then it would be brom cresol green. That would be your indicator of choice because it brackets the equivalence point. And the equivalence point we get just by taking the average of the starting and ending positions. Any questions about number 3? Generally, people don't have too much trouble with that one. All right, I'm going to re-roll, and let's take a squiz. Let's take a squiz at, whoops, I need to end exit preview here. Yeah, oh, sorry, I need to get this down here. Oh, come on. There we go. Okay, we'll re-roll this one and we'll do another example of number 2. I tell you, if there's one thing that people have trouble with, it's that. It's these reactions. But again, it's one of those things, if you do it enough times, you'll see the pattern and you'll begin to understand exactly what's going on with them. See what this one is. All right, so CH3Li plus LiHCH3. Why don't you all try that? Try that yourselves, and then I will put down the answer here. So give that a go. See how you're understanding it. I'll give you a minute or so. Now, whether it's a strong acid or a weak acid or a strong base or a weak base doesn't really matter, but it does matter if it's an acid or a base. That can really affect what's going on here. I will warn you that this one's a little tricky. We'll see how it goes. So we've got the CH3. Whoops, where are we? Here we are. CH3Li, and we've got the LiHCO3. Okay. Now the CH3. Go on.
Is this one tricky because it's a weak acid and not a strong acid?
No, it's tricky. It's tricky because what I'm going to do with this weak acid is going to be a little bit unexpected.
Okay. Well, you made a point earlier of saying that weak acids, hold on, what was I looking at? I lost it, but you were talking about how you asked, do we understand how, I'm sorry, the strong acids, how do we get the strong acids, their parts?
It really won't matter.
Okay.
Rebecca, if it's an acid, it's always going to split up the same way. We're always going to get that H plus out of the acid, which is what's kind of tricky about this one. With the base, I know it's going to split into CH3 minus and Li plus, but the acid is going to split into H plus and then LiCO3 minus. So then when they join together, we get CH4 and we get, and then we get Li2CO3. So what am I doing there? I'm just doggedly following my pattern. If I've got an acid, I know it's going to split into H plus and whatever else is going to be a negative charge. And then that joins with whatever's on the other side that's positive. Anybody got any questions? You all completely understand that, hey? All right, let's leave. We'll re-roll. We'll do one more. Okay, HClO4, KNH2. And we're told that HClO4 is a strong acid, but again, all that matters is it's an acid. And then we've got a strong base here as well. That's going to be H plus and H plus, ClO4 minus. And the other part's going to be K plus and NH2 minus. And you'll see that that's going to join with the ClO4 minus, and the H plus joins with the NH2 minus, and we get NH3 plus KClO4. The order of these doesn't matter, by the way, in the answer. You can do it either way.
And what about in the question? Does it have any bearing?
No.
Like in the reaction side?
No.
Okay.
No, because this is what's happening at the equivalence point. So what we're saying here is that they're in equal amounts anyway, and it just whether the acid is first or the base is first is of no import.
And when things are being titrated together, are they written in a certain way in an equation?
No, absolutely not. You have to be told.
Okay.
You'd have to be told in the actual question what was being titrated with what.
Okay.
All right. Does anybody have any other questions about question 2? So what's the best way of handling that? I would just do question 2 again and again until I was getting the right answers for it. And that's how I'd handle it. Because it's really important you see this pattern, that you understand exactly what's going on with it. All right. Let's move on here. We'll look at question 2 on the. Let's see if I can move this around a little bit here. So question 2, again, I'm not going to go into a whole lot of background with this. I'd expect that you'd watch the video in order to really make sense of this. You guys are kind of lucky because when I ask this in a pen and paper test, I can harass people about the partial charges. And one thing I haven't done, and that's really a shortcoming here, is that I haven't been able to come up with a question that actually allows you to specify where the partial charges are on anything. That's going to be a real challenge for me in the future. But that's one of the real important points about what's going on with this question, is being able to figure out what's going on with those partial charges. So when we're looking at this kind of problem, I will say there are 4 kinds of scenarios that we deal with. And I'm just going to summarize them over here. Let me see. I'll call this scenario 1. And I say this is where the negative charge is on a is on a completely different atom. Number 2, we got this scenario here. And I call this distance. Actually, I'm going to change that up a little bit, if it'll let me. I'll include the anions rather than just the original compounds. And that might make a little more sense. Yeah, I'll call this distance. Scenario 3. And let's see. And in this case, X and Z are in the same position, but they have a different electronegativity. And this one here. So I'll try and keep this a little bit consistent. I'll take that one off there and I'll put the extra X on this one. There we go. Rather than more, I'll say greater number of electronegative atoms. And what's happening here is that if you've got this kind of arrangement, these lines represent bonds between C's, but the C's aren't mentioned. So this is if you've not seen this before, that's what those points all represent. They all represent C atoms. So if you've got this CX bond here, and I draw it out, the X is more electronegative than the C, which means that if you were to draw a bond between them, which would consist of 2 electrons, the electrons would be closer to the X than they are to the C, which allows us to put these partial charges on, which will enable us to figure out the difference in stability between these. I'll stop here for a second. Does anybody have any questions about these partial charges? Because that usually annoys people a lot, these partial charges. Okay. So what that means is we got a delta plus here, a delta minus here. We got a delta plus here and delta minus here. This is something I'd really like to be able to test people on actually in this environment, but I haven't figured out how to do it yet. If anybody comes up with an idea, I'll be more than happy to listen to it. I'll tell you what though, I won't institute it this semester. I'll just victimize other students in later semesters with it. So if you come up with something, let me know. Might be some extra credit in it for you. All right.
I'll be taking you for organic chemistry, so that's not going to be happening.
All right. Okay, but you can see here in the distance one, look at where the delta plus is relative to y minus in each case. And you can see that if you've got something positive and something negative and they're closer together, that's going to be a greater stabilizing force than when they're further apart. And that's what scenario 2 is predicated on. And in scenario 3, let's say, I'll say X is more electronegative. That means that that would have a bigger delta minus, a big delta plus, and Z would have a little delta minus, a little delta plus. And you can see in that instance then that there's less stabilization in the second one if X is more electronegative than Z. And in the case of scenario 4, we'll have a delta minus there, delta plus. And here we've got delta minus. And because there's two of them there, we can say there's 2 by delta plus, and that will stabilize the negative charge more. So that in that case, then it would be the second one would be more stabilized. So the whole premise here is based on anion stability, and the logic here is that if you've got two compounds, I'm calling them AH and BH, and they split into anion and H plus. The anion, of course, being the negatively charged species here. If A minus is more stable than B minus, we're also going to get more H plus. If we get more H plus, it means it's more acidic. So that's the very quick and dirty way of explaining what's going on here. Does anybody have any questions? So can anybody tell me what scenario we're dealing with in the question I have on the screen? 1, 2, 3, or 4? Anybody want to guess?
Is it 3?
Yes, it's 3 because they have this, when you split them apart, I'll enlarge this. They look like this when you look at the anions. The anions are very easy to find actually once you look at them. And it'll split into H plus in this way. And you can see here, it's based on the I and the Cl, which have different electronegativities. Cl is more electronegative than I. So this one would end up being more stable, which makes this compound here that I'm pointing to more acidic. All right, does anybody have any questions about number 2? Yeah, I think, honestly, I feel like with number 2, it's a bit too easy to kind of just, I don't know, fudge your way through it a little bit in the questions I have on the test 2. It's one I'm not very happy with about the way I'm testing it, because I think it's too easy to get through it without really understanding what you're doing. Especially if I give you a sheet of paper, which I do, to allow you to write stuff down, then you can just fudge your way through it. But I'd really prefer you, obviously, that you did understand what you were doing, because it does matter, I think. But that's my challenge. I've got to come up with something that's a bit more comprehensive, I think. Okay. So for question 4 here, it says which compound is more acidic? And when you're doing that, I'm just going to try and keep this here, but just remove some of the other stuff. What you're doing is you're trying to figure out which scenario would matter the most here. And you can see that one has an electronegative atom on it and one doesn't. So the one with the one to be more acidic would be the one, this is really like, it's scenario 3 effectively, where you've got an H versus a Cl. So you see you've got the Cl here versus an H here. The Cl is more electronegative than the H. So that's going to stabilize the anion more. which means that this one would be more acidic. Does anybody have any questions about number 4? Okay. This is a similar question. Which compound has the more stable anion? And you can see, again, the one with the electronegative group versus the one that doesn't would have the more stable anion. So this would be the answer here. These ones, you kind of get used to the pattern fairly quickly, I think. Okay, look at these two in question 6. Which scenario, just looking at the scenarios 1, 2, 3, and 4, do you think is the relevant one? Anybody have any idea? You could possibly write the anions down, but I don't think it's necessary. I really don't.
I was thinking 4 because it had more.
Yeah, one has more on it than the other one does. So I would say it's scenario 4. And the one that matches that is a greater number of electronegative atoms attached to the given point in the anion. That would be the reasoning for that one. So what I'll do now, it seems like some of you have trouble figuring out which scenario is which. I think that's important. So I'm going to go back here. I'm going to exit here. And I'll show you one of the resources I have here in the relative acid strength folder, this one here. I have these acidity problems. I'm going to pull up this supplementary acidity problems here. The other one has similar problems on it. Okay. So let's see if we can figure out the scenario that matches on in each of these cases here. Okay, so number 1. Now, if it helps, you figure out where the anion's going to form here. So which scenario do you think matches number 1? Any thoughts? All right. I feel like I've lost you all here. Can somebody give me some clarification as to what I can do to make things a bit easier for you here?
Maybe a step-by-step, like when I'm looking at number 1, how to observe it or break it apart. I mean, I'm thinking it is scenario number 1, just because they're different and the OH is negative.
Right. Yeah, that is true. All right. It might be helpful, I guess. We'll see. Hang on.
I'm personally just not fully understanding what differentiates each scenario.
Okay. All right. Let's look at the first one then. I think what I would do, and I am shortcutting it a little bit here, that's why, is split out the anion, what the anions look like for each of them. Now, to form the anion, all you have to do is remove H plus from it. And then the negative charge forms wherever the H plus is removed. All right, so then you can hopefully see that it matches a scenario 1 because you've got O minus versus NH minus. Now, the reasoning behind that is that if O is more electronegative than N, it means that O negative will be more stable, which means that the compound it came from, which is this one, will be a stronger acid. It will produce more H plus. So that's why scenario 1 would work on that one. So the first step you should do here is to remove the H plus and leave the anion so that you can see what the anion looks like. And maybe that makes things clearer. Now take a look at number 2. Can anybody tell me which H would be removed? For number 2, where the H plus would come off? Any guesses?
I'm assuming the OH.
Yeah. Yeah, and again, it's a question of electronegativity. OH is more acidic than CH. These are all CHs, but O is more electronegative than C, so the H will come off the oxygen there. Yeah, I do apologize for this because I guess I'm hoping that the videos are clear enough, but you know, if they're not clear enough, then you need to seek some guidance from me. Okay, let's have a look. So this one here, again, you take off the H. Okay, so what scenario would match that case there? 1, 2, 3, or 4?
I think distance. They're all the same, but one is closer.
Right. The F is in a different location in one relative to the other one. So it's scenario 2. So I'm going to put you other guys on the spot here. Nathan, do you see that? Do you see how to recognize that? Okay. What about you, Nee? And Jacob? I don't know if you can talk or not.
Yeah, I see it.
In this one.
Okay, Jacob, you all right as well? Okay. All right, look at number 3. And again, we're just going to follow the same thing. I'm not going to write down these anions. You're going to do the same thing. Which scenario is going to match for number 3? That's this one here. One at the top. Which scenario is going to match? Look at where the difference lies.
Would that be 4?
Yeah, it would be 4. And the reason is because one has 1 F and one has 2 Fs. If he has 2 Fs, it's going to have a greater delta plus right here, which is going to stabilize the anion over here. There's no difference in distance or anything here. They have the same number of atoms, but have a different number of atoms, but in the same location for that. Anybody got any questions about that? All right, what about number 4? What scenario are we looking at for that one? It's not distance because you can see they're in the same location. It's not the different numbers, and you can see it's going to be O negative and O negative, so that only leaves one possible scenario, which would be scenario 3. Is everybody okay with that? A different electronegative atom located at the same point. Okay. Let's look at number 5. Now, number 5 is a little bit tricky. What scenario are we looking at for number 5? Does anybody want to take a guess? Nee or Jacob? I'll put you on the spot here. Do you want to take a guess at which one it would be? Well, it's not going to be scenario 1 because the negative charge is going to be on the same atom. But they're both on the CH2 minus there. All right, so for that one, it would be, I'd say it's scenario 3 because they both have 3 Fs. I'd say 3 electronegative atoms. They're all connected at the same point, but they're different electronegative atoms. So you've got F versus Cl essentially. The fact there's 3 of them doesn't matter, but the fact that they're different atoms does. And the one that would be more acidic would be the one with the Fs because the F is more electronegative than the Cl. All right, what about number 6? Anybody want to guess about number 6? Any thoughts about number 6? Look where the, go on. Go on.
2.
Oh, what was that, Nee? I'm sorry?
Scenario 2.
Yeah, that's right. It's distance. Yeah, because you've got the Fs in different places. Okay, for extra credit, Nee, well, as a joke, sorry. Which one would be more acidic? The one on the left or one on the right?
I'm not sure. The right?
Yeah, the right, because the F's are going to be closer to where the negative charge is. The negative charge will be on that N once you take off the H plus. So whatever's closest, that's going to be the more acidic one. So I'll write that underneath each of these. That's going to be more. If X is more electronegative to zeta, it'll be more stable. That's more stable. And we'll say if X is more electronegative than Y, then this will be more stable. And if this is more stable, it means the acid it came from is more acidic. And let's see, this one down here, this one would be more stable. So that helps as well, I think, if we do that. Okay, let's have a look at, let's see, number 7. Well, that's pretty similar to number 5, actually. So you've got the same, you've got the Fs and the Br in the same location, but because F is more electronegative than Br, that makes the first one, the one on the left, more stable once you take the negative charge on the end there. So that would be scenario 3 for that one as well. So it's going to be a matter of being able to look at those 4 scenarios and be able to figure out which one matches the case that you have. And after a bit of practice, it's actually not that bad. And then be able to say, well, which one's going to be more stable, and therefore which compound is more acidic, the one that came from is more acidic. All right, does anybody have any questions?
I just want to make sure I wrote this correctly. It's more, if it's more electronegative, it's the more stable, and so more acidic.
So the compound, yes, but you see that the anion isn't acidic. It's the original compound that's more acidic. I think that's important to note, Rebecca.
Okay. Is it the compound with the more electronegative anion that is more acidic, or no?
I would say that the anion that has the more electronegative atom will generally be more stable, which makes the compound it came from more acidic.
Okay.
To be very to be really picky and accurate. That's
precise.
What I would say.
Okay.
Yes.
Okay. All right. Thank you.
But again, for you all, it's a matter of being able to look at these and figure out the scenario, and then figure out which one is going to be more stable as an anion, and then that will tell you which compound is more acidic. Now, the fun quiz is also useful for that as well. The extra credit quizzes that are in that folder. They're pretty much the same questions anyway, I think. All right, so let's go through these and we'll see if we can get a bit more clarity here. All right, looking at question 4, which scenario do you think we're dealing with? You should be able to tell me easily now. We've been through that. Which scenario do you think it is? 1, 2, 3, or 4? No thoughts?
This is tricky for me because it looks like there's a different number of hydrogen atoms, and then the chlorine is moved. So
yeah. Well, you see, so then it's about distance, isn't it? The number of hydrogen atoms really doesn't matter. But look, you know, I think what's important when you're looking at that, and this is what I would do. I think you all might be overthinking it a little bit. But what I would do with that is I would draw out what it looks like as anions, and we know that the anion is going to be the one it's going to be on the O. So this is what they would look like. Do you see there's still 4 hydrogens on each of those, Rebecca? In each compound? 3 plus 1 is 4, 2 plus 2 is 4. So there's no difference there.
Mm-hmm. Okay. Yeah, I do see that now.
Yeah, but what's important is look at the let's put these partial charges on, and you can see it's going to be distance. It's going to matter. So you got the delta plus with the O minus and the delta plus with the O minus. All right. Does anybody have any questions about that? So which compound is less acidic? Which one would it be? The first one or the second one? Less acidic.
That is less acidic.
Mm.
Would have to be, I'm thinking the top one. I'm sorry, the bottom one that's farther away.
That's right. Yeah, because the Cl is further away, which means the delta plus is further away from the negative. Doesn't stabilize
It's less
it as much.
stable.
Yeah,
right.
so the anion's less stable.
Okay.
Which makes the compounds, and the compounds you see there, less acidic.
Okay.
Less willing to give up that H plus to form the anion. Yeah, so that's a bit more challenging. All right, which compound has the more stable anion? So for something like this, let's see, I will get rid of what I've got here. It's asking specifically about the anions, so it makes sense that we should take the H plus off here and see what we're left with. In each case, let's see, we've got, this will be F minus and H plus, and this will be NH2 minus. I'll put on the other side here, and H plus. So it's asking which one has the more stable anion. The one that has the more stable anion will be the one that's more electronegative. And out of F and N, F is more electronegative. So the top one would be the more stable, would have the more stable anion. It's all based on electronegativity. So just out of curiosity, does anybody know what scenario we're dealing with that one? Anybody want to guess? What scenario we're dealing with number 5? Any thoughts?
I'm assuming number 1.
Yes, that's right, because the negative charge is on a different atom. We've got F versus N. In all the other cases we've dealt with, the negative charge has been on the same atom. And one thing I'll tell you is, in all of these cases, it's only ever one thing. I never combine scenarios, so it's only ever one scenario that we're looking at. Does anybody have any questions? Okay. Let's look at, this one here. Which scenario are we dealing with in these two cases here? We've got the top one and the Cl and the Br here. Which one is going to be which scenario we're looking at?
Is that scenario 3?
It is, because we have the negative charge will be on the oxygen in each case. So it's not scenario 1. And they're in the same place, so it's not scenario 2. And they have the same number of atoms, so it's not scenario 4. So that only leaves scenario 3, which means we've got a different atom on each one. And the scenario would match that. Let's see. It's not closer. The negative charge is on a different atom. Nope. An atom attached to the anion is more electronegative than an atom attached to another anion. So it'd be that one. That's how it would match for that. All right. Does anybody have any questions about that?
Just in terms of determining electronegativity, are we allowed to have a periodic table with us while we're doing the test?
I think there's one in the test. Oh, there isn't. I tell you what, I will add a periodic table to the test, Nathan. And if I don't do it, harass me. I'll add it to both. I'll add it to the graded copy and the ungraded copy. Fair enough?
Thank you.
Okay. I'll fix that after we get off here. I'll add a periodic table. I didn't think it would be useful for this particular test, but I think for that reason it would be with the electronegativities.
Yeah, it just helps to see the trends.
Sure. All right. So what's the correct statement that links acidity to anion stability? So this is where the semantics of what I was talking about comes into play here. So for this one, I'm looking at it and I can see that if I drew the anions out, and I will draw the anions out for this one. The anions are going to look like this. One will be CH3, CH2, CH2 minus NH plus, and the other one will be CH3, CH2, NH minus NH plus. And we've got A and B here. Okay, so the question is, the anion, what's the correct thing here? Well, first of all, look at them and determine which one's going to be more acidic. Does anybody want to guess which one's more acidic, A or B? Based on what I've got here. Anybody want to guess? Well,
Maybe B.
It's going to be B. Yeah, B is more acidic because it's got the more stable anion. And the reason the B anion is more stable is because N negative is more stable than C negative, because N is more electronegative than C.
Yay, that's what I was thinking.
That's good. That's good. All right. So that's fair enough. Now, if we already know that one's going to be the more stable anion, and it's going to make this one more acidic, which is good. So now I've got to figure out which one of these matches. And it happens to be the first one. The anion of B is more stable than the anion of A for the reason I just said. So the compound B is more acidic than compound A. And I think that's an important concept for you all to make sure you understand. All right, does anybody have any questions? Okay. All right, so yeah, we're at 11 o'clock. We'll continue here. I'll look at the Ka, Kb calculations here. Now, just very briefly, I'll go through some of the calculations you'll be looking at here. So first of all, if we've got a compound AH, it's splitting into A minus and H plus, then we know that the K or the Ka is going to be A minus H plus over AH. So it's something similar to what we did in test 1. We're writing out the K expressions. And this is what distinguishes Ka and Kb. Make that a little bit clearer. There we go. So the A here stands for acid, which means that we're looking at H plus as a product. That's the most important thing there. And for B, the B stands for base, which means we're looking at OH minus as a product. Now, but what you need to understand here is that the acid can be expressed one of two ways. We can include the water or not. And it's simpler not to include the water for the acids. We end up with just A- and H+. But if we're dealing with a base, we have to have water in there. But you'll notice the water doesn't appear in the K expression, the KB expression. We ignore it. That's because the concentration of water isn't going to change significantly. So it's kind of tied in with the constant. But again, if we do include the water with the H+, that's fine, but then it becomes H3O+, which is the same as H+. So that's going to be important as well. So H+ is equivalent to H3O+. So whether we use water or not, and you'll see throughout this whole section, I use them interchangeably. Sometimes I'll include the water with the acid, sometimes I won't. But with the base, I'll always include the water. And the reason for that is because it's the only way I'm going to get that OH-. I have to get that from the water. So that's a bit of an annoying thing, but that's how we do it. Does anybody have any questions so far about the Ka, Kb? So before we get on to the calculation of this, I'm going to skip ahead a little bit to the reaction questions. That's these questions 12 and 13. Where what it's doing is it's asking for what the Ka or Kb questions, reactions will look like. And in each case, for consistency's sake, I have added water into both of these, both the Ka and the Kb. So I wanted to show you how to get those first, and then we can look at the actual reactions, and you'll be able to see how we manage those. Okay, so let's look first of all at this one here: CH3NH- plus H2O. And we're after here Kb, it says. So automatically, I'm going to write down OH- over here, but I think it says to put the OH- second, so I'll abide by the instructions there. So Kb. So it's going to be something plus OH-. Now I know it's plus OH- automatically because it says Kb. It's that simple, folks. If it's Kb, it's base, it's OH-. If it was Ka, I'd put H+ or H3O+ in the case of adding water. So how do I figure out that other mystery product there? Well, this is a little tip for you. Think about the water as being a combination of H+ and OH-, which kind of it is. I mean, if you were to do any acid-base reactions, you know that H+ and OH- combine together to give water. But if you think of it as being OH-, then you can see that that's where the OH- ends up, and the H+ combines with the other thing, and we end up with CH3NH2. So that'd be the answer to that. But look at the charges there. N negative H+, so we end up getting a neutral compound there. Oh, this absolutely kills students. The combining together of these anions and cations to get the different charges, it's killer, really is. Any questions about that? All right, let's look at the next one, Ka. So we've got CH3SH plus H2O gives H3O+, right? So if it's acid, this is Kb, that produces OH-, and the Ka, that will produce H+, but in the case where water's added, it'll be H3O+. So we know we're getting H3O+ here. So the product here is going to be, well, where'd the H plus come from? Well, it came from the CH3SH, so it'll be CH3S minus plus H3O plus. So that's where the H plus came from, that went on the water. So think of the H2O being added to H plus, that's where the H3O plus comes from. And you can see here, this becomes CH3S minus. Any questions about that? Oh, sorry, it's pH, isn't it? I'm sorry about that. It should be pH. Not going to really change anything, but it's not CH3, it's pH.
I guess I feel a little bit confused if it were just the H plus, and not the H3O plus. Hopefully one will come up where we do it like that.
Well, they won't. They're all going to be water. But if it was, it'd look like this. It'd be very similar. It's going to be the same anion. That's how it would look if there was no water involved, Rebecca.
Okay. Okay.
I can give you I'll give you all a couple of rules of thumb here, which I will do since you're here and you're trying to figure out these kinds of things. So let's say, and I'm just going to make this very generic. Let's see. This is for KB. Let's see. Oh, how would I express this? So this is always this is the pattern. It never changes. Okay. So B will have a certain charge on it. It could be neutral. Okay. It could be neutral. It could be anything, any charge. But what's important is that the product here will have an extra H and the charge will go up by 1. So let's say, just as an example, let's say I make this X -2 plus H2O. Can anybody tell me what mystery compound would go in there following that thing there? And I'll tell you, I'll lay it out again. Add an H and put the charge up by 1. What would it be?
XH minus.
XH minus, exactly. See, it wasn't a trick question. Right, that's because you're effectively adding H plus to whatever you're adding here. All right, well, let's say it was X plus H2O. What would be the mystery compound then?
Would it be XH plus?
Sure. What's the rule? You add the H and put the charge up by 1, right? It's like magic, isn't it? It's like magic. Honestly, it's foolproof. It's absolutely foolproof, what I'm telling you here. Gee, I wonder what the other one's going to look like. Oh, let's look at the Ka. Let's see what's going on with that. See if I can come up with something for that. Ooh, Ka. So B plus H2O gives something plus H3O plus. We'll say B charge. I'll do the same thing. I'll say BH. And you can see here, you take away the H. And the charge goes down by 1. I'll be blown. It's almost like it's the exact opposite of KB. Right? Well, for the KB, if you remember, you add an H and the charge goes up by 1. If it's Ka, you take away an H and the charge goes down by 1. All right. So let's have a look. Let's say you've got XH3 plus H2O gives H3O plus over here. What's the mystery compound that goes along with that?
XH2 plus.
Yeah, or I'll make it HX2 plus. Same deal though, yeah. Yes, HX2 plus. And if you look at the math here, we've got 2 plus and 1 plus, that gives 3 plus. You see, all of the time, these things have to balance. All right, let's say it was HX plus H2O plus H3O plus. What would be the magic compound there? Take away an H, charge goes down by 1.
Would it be X negative?
Yep, X negative. And you can see it works out. X minus and plus, that's neutral. It's neutral on that side as well. So not only do they have to be balanced for the atoms, they have to be balanced for the charge as well.
When we're writing out charges, like in answers, do you want us to specify a 1 before a negative, or does it like not matter in terms of what's considered correct by the test?
Well, again, if you did put a 1 in front of it and it marked it wrong, you could always email me, right? Because it always tells you the answers.
Gotcha.
Right, but I will tell you, in general, I don't put a 1 in front of the minus. But you could, if you wanted to, and then I would fix it because it's not wrong. All right, anybody got any questions? So you can see that's how you're going to do all of these. And look what we did here. This is for the acid. So we add the H, and it goes up by 1, so it becomes CH3NH2, and it'll be neutral because that's negative and goes up to neutral. And for this one here, this is for Ka, we take away the H and charge goes down by 1, so it becomes PHS minus. That's how you do it. Once you get that pattern, it's actually not too bad. It really isn't. Does anybody have any questions?
No, but that was super helpful.
All right, let's take a look at these questions here, 8 through 11. And we're calculating the actual Ka and Kb. And we're using actually a similar process to what we talked about back in test 1 when we were doing equilibrium constant calculations. We did it for question 4 of test 1, if you remember. And if we got XH and we're looking at Ka here, and if we were to do the reaction, it would become X minus plus H plus, or this works as well. H2O plus XH gives X minus plus H3O plus. So either of those is going to work fine for what we're doing here, because these two things are the same. And we do an initial molarity, and then we do equilibrium molarity. We did this last time when we talked about question 4. So the initial is going to be 0.84, and we'll have 0 and 0 on the products. And then here, we're going to have 0.84 minus Z, and that's going to be Z and Z. All right, so we did this last time in test 1, so I'm hoping you'll remember that. Does anybody have any questions so far? Just in a very, very elementary way, I'll tell you what's going on. You got XH, you got XH, you got XH initially, and then let's say two of them broke apart into X minus and H plus, you can see that the XHs go down by the same number as the X minuses and the H pluses go up. So really don't overthink it. That's all I'm really saying. That's what the Z's are. It's just how much it dissociates, how much of it breaks apart. So that's a very, very elementary way of looking at it. So we have to find Z, and what we're given here is the POH. Now there's a couple of things we're talking about here. Now pH, definitionally, is the negative log of the hydrogen ion concentration. Which means that if we want the hydrogen ion concentration, it's going to be 10 to the negative pH. That's because the inverse log is going to be 10 to the power of. That's how we're getting that. Likewise, POH is the negative log of the OH minus concentration. See, the little p there just means take the negative log of. And in class, I always make this joke. It's pH is negative log of H plus, POH is negative log of OH minus, pKa is negative log of the Ka, pKb is negative log of the Kb. P grandmother is take the negative log of your grandmother. It's the same deal. You know, it's just take the negative log of it. And then if you want to get the actual original thing back, it's going to be 10 to the power of that negative. And the other rule that's important there is pH plus POH is equal to 14. And it's not a coincidence that that matches the top of the pH scale. Now, I'm not going to go into the nuances of that. I mean, it's in the video, but those are the important formulas you're going to need here. All right. So looking at this, we've got in question 8, we're given a POH, but what we're looking for is an H plus. So we're going to have to do some adjusting here. We have the POH, so I think we can solve for the pH. Well, I'll just say that pH is equal to 14 minus the POH, 14 minus 12.3, and that's going to be 1.7. And then from there we can get the hydrogen ion concentration, which is going to be 10 to the negative pH, which in this case would be 0.0199 or 0.019 or 0.020, we'll say, molar. So that allows me to calculate the Z value here, which is going to be 0.020. That's going to be 0.020. And this will be 0.84 minus 0.020, which is going to be 0.82. So at the end of that, I'll go ahead and I'll enlarge this a little bit here. We can do our Ka expression, which is going to be X minus times H plus over the XH, and that'll be 0.020 squared over 0.82, and that's going to be my answer. All right, anybody got any questions about that?
What is the symbol And the Ka expression at the bottom, the denominator.
Oh,
Is
it's,
that
sorry, it's X.
XH?
It's X.
Okay.
It's XXH.
That's it. Okay,
Sorry
thank
about
you.
that. Yeah. Now you'll notice that if we've got Ka, we've got Kb, we've got Kb, and we've got Ka here, and we've got these different combinations of POH and pH. So let's look at the next one. And you'll see sometimes we have to do this subtraction and sometimes we don't. Sometimes we don't have to do this subtraction. So I will give you a general rule in a second. See, this case we had to do the subtraction. Let's look at the next one. Actually, I'll look at number 10 just for kicks. Look at number 10. We'll come back to 9. But looking at number 9, we've got Kb here, which is X plus water. Actually, I'll do the water plus X and make it look a little bit prettier. Doesn't matter which way you do that, really. So according to our rule earlier, we get XH plus OH minus as our products there, if we're looking at Kb, and we're expecting the OH minus, of course, because it's Kb for base. And the initial molarity here is going to be 0.51. Sorry, no, we're looking at number 10, yeah. Number 10, 0.51. 0 and 0. Then it's going to be 0.51 minus Z, Z, and Z. And if you look here, what we're given is the POH is equal to 12, which means that we can get the OH minus directly. We don't have to do the subtraction from 14. So it's 1.2, I'm sorry, not 12. 10 to the negative 1.2. Which is going to be .063 molar. So that becomes our X value there. So our Z value, I'm sorry. Z, Z, and this will be 0.45. And again, then we would just do what we did earlier with the Kb, which would be XH plus OH minus over X. And then we just sub our values in, 0.063 squared over 0.45. That'll be our Kb value. So your question's going to be, well, when do you have to do the subtraction from 14 and when don't you, right? That's what you really want to know. So as a general rule, this is what I would say. I would say that if you're dealing with Ka and you're given pH, then no subtraction. If you're given Ka and POH, you will have to do the subtraction. If you've got Kb and pH, you'll have to do the subtraction. And if you've got Kb and POH, you don't have to do the subtraction. But you can, hopefully you can see why pH would lead to H plus. POH would lead to OH minus. And then that needs to go to the H plus. Likewise here, if you're given the H plus, you need the OH minus. And here for Kb, you get the OH minus, so you don't have to subtract anyway. So remember that Ka gives H plus and Kb gives OH minus. That's the bottom line. Does anybody have any questions? So remember, I do have the video solutions to all of these as well, and that can be helpful too when you, at least going through it the first few times, you get to see this pattern. But I'm trying to explain to you why that pattern exists, so you don't have to just memorize it. Does anybody have any questions? All right, so for question 9, I would hope that you see you've got Kb and you've got pH. So you would have to do the subtraction there, so you could get the POH and get the OH minus from there. And likewise in question 11, we've got Ka and we've got pH, so we wouldn't have to do the subtraction because that will allow us to get H plus directly. So it all comes back down to those equations I had earlier that I've erased now that relate the H plus and the POH and the pH and the POH. All right, does anybody have any questions? All right, well, since this one is a bit longer, what I'm going to do is, I think I'm going to do another Zoom session on Thursday at the same time. So I'll do another one at 10. I'll send out an email and I'll add an extra one into the Zoom folder, because I think that I'd like to see a bit more action here on this. It gives you a chance to go through these questions we've already done today, and then you can attend on Thursday or watch the one on Thursday. All right, and then we'll leave it there for today, and we'll continue on Thursday at this point. Anybody got any questions?
No, but thank you.
All right, you're welcome. Yeah, this one's just a bit more intense than the previous one. There's a bit more calculation, a bit more stuff to go through. All right, well, have a good day, folks, and I will see you all. Well, hopefully I'll see you on Thursday. Okay, thanks. Bye.